Thank you for the introduction. Okay, so first off, what is a blind signature scheme? So we've seen many different types of signature schemes in this session, and let me explain now what a blind signature scheme is. So in the context of blind signing, we have a signer, S, on the left side here, and it holds a secret key, SK. And on the right side, we have a user, U, that holds a public key, and it holds a message. And so now, the idea is that the signer and the user are going to run this interactive protocol, and at the end of the protocol, the user is going to hold a signature sigma on M that anybody can verify using the public key. Okay, so note that in comparison to regular signing, the signer here is not in possession of the message. Okay, and as it turns out, this is actually the crucial feature of a blind signature, and we express this via the blindness condition. Okay, so blindness says, informally, that the signer is actually not allowed to know what message it is signing. This is why it's called a blind signature. We can even make a stronger statement that says that if the signer engages in many of these runs with the user of this interactive protocol, and afterwards gets to see all of the signatures that it created during these runs, then it cannot link the signatures to the protocol instantiations in which they were created. Okay, so this is the first security requirement. And the second one, of course, is that you should not be able to sign a message without the help of S. But as it turns out, it's a bit tricky to define the second property. So let's actually take a bit of a closer look here on the second slide, what it means. So we formalize unforgeability in the context of blind signing via this one more unforgeability experiment. Okay, and here we're looking at an adversary on the right side, which is basically taking the role of the user in this blind signing scheme. And it's going to be running this blind signature protocol L times with the signer S. Okay? And it is considered successful in forging a signature if it can come up with one more signature and one more message than the number of signatures that they could have seen by interacting with the signer. So now, why do we have to formalize it this way? Why can't we just rely on the regular existential unforgeability notion? Well, because the signer doesn't see the messages that it is signing. So it cannot check which of them is fresh in the end. And this is why we need to formalize it in this more complicated way. Okay, so here's just some basic motivation for blind signatures. They were originally introduced by David Schaum in 1983, and they served as the basis of his anonymous eCash system. And so the idea is very simple. So we have coins, and basically the coins are blind signatures, and the users can trade them for goods. Okay, and of course, only the bank here, which is centralized, should be able to issue these coins to the users. And this, of course, is ensured by unforgeability of these blind signatures. And now the second property that we would like from cash is sort of the physical attribute that cash has, which is that it is untraceable and anonymous upon spending. And this can be ensured via the blindness property, which basically says that when a coin is spent, then the bank cannot link it back to a particular issuing of this coin. Okay. So here is sort of an overview of the compact blind signature schemes that you can find in the literature. So I should say that there are also blind signature schemes from more general complexity assumptions, but they tend to be not as compact and not as efficient as the ones that I've gathered up here. So on the left side, we have two-move blind signature schemes. Okay, and on the positive side, they're very efficient, and they allow to sign polynomially many messages per public key, and even in a concurrent fashion usually. But on the downside, they rely on stronger assumptions, which typically include one more type assumptions. Okay, so, and on the right-hand side, we have these three-move blind signature schemes, so there will be three interactions between signer and prover, so they're a bit less efficient. But on the positive side, they follow from standard assumptions, such as RSA, factoring, and DLOG. On the downside, however, and this is much more a caveat than the three moves here, is that they only allow for a polylogarithmic number of signatures to be issued per public key, and after this they become insecure. And it turns out that this is actually optimal. So if you issue more signatures, then you can show an attack on this. But it doesn't mean that these signatures are useless. You can use them as building blocks for more complex schemes, and so it still makes sense to consider them. And this is what we're going to be doing in this talk. So I'm going to focus on the schemes here on the right side. So far, they were mostly considered by Poincheval and Stern in their seminal paper from 2000, Journal of Cryptology. So our contributions are, so we show in our work how to build any such three-move blind signature scheme from a linear hash function, which is basically a hash function which has some homomorphic properties. And I will show this in the next couple of slides. And secondly, we modularize and simplify the proofs from these works by Poincheval and Stern, which I've listed here. Okay, so this is the roadmap. So to do this, we give this generic framework, which I've sketched out here, okay? And it has two steps. I'm going to explain the first one first. And basically, it's going to show how we go from a linear hash function, which I'm now going to define, to a linear identification scheme. And the second step shows how to go from a linear ID scheme to a linear blind signature scheme. Okay. So first, let's look at linear hash functions. So we're going to consider a domain and a range, D and R, and we're going to be assuming that there are S modules. Okay, so they commute with this structure S here. So we have a function that maps from the domain to the range. And as I said, it has this linearity property. And what it means is that for all x and y in the domain of D, and for all scalars S in this set S here, we have the property that f evaluated on S times x plus y is the same as multiplying S with the image of x under f plus f of y. Okay, and of course, they wouldn't be hash functions if they weren't compressing, so this is also a requirement, and they should also be collision resistant. So now before I show how such a hash function directly implies an identification scheme, let me actually recall quickly what an identification scheme is. So we're going to consider three-move identification schemes for this talk, and here we have a prover on the left-hand side. Again, the prover holds a secret key, and on the right-hand side, we have a verifier that holds a public key. And the goal of this three-move interaction is for the prover to prove to the verifier that indeed it holds the secret key matching this public key. So it follows, the structure of this protocol looks as follows. In the first round, the prover sends a commitment to the verifier. Then the verifier picks a random challenge, sends it back. And then there is a response S by the prover. And now the verifier can either accept or reject this answer. Okay. So this is how an identification scheme looks. So now let's look at how such a linear hash function directly implies a three-move identification scheme. So how does it work? So let's consider such a hash function. So now the secret key will just be some point in the domain, and of course the public key will be the linear hash function evaluated on this secret key. Okay, and the goal of this identification is now to show that we know the pre-image of pk under f. So to do this, you first pick a random r in the domain, then you evaluate the function on r, and you send over this commitment r. Then the challenge will be some random point in this set S, send it over, and then S is going to be computed in the domain as r plus c times the secret key. So you send over this answer S, and then the check is going to be if f evaluated on this answer S is the same as r plus c times the public key. And of course, because the linear function has this homomorphic property, this check should always evaluate to true, and the identification scheme that results in this way has perfect correctness. Okay, so now I'm going to introduce a new security notion on identification schemes, and later I will explain how this security notion is going to be tied to the one more unforgeability notion that I showed in the beginning of the talk. So we call this security notion one more man in the middle security. So what does it mean? So we consider here an adversary that acts as a man in the middle between the prover and the verifier. So it forwards back and forth the communication between these two entities. So now it gets to run L times this identification scheme with the prover here on the left-hand side, and its goal is to close one more of these interactions with the verifier. And so, of course, this is a very natural notion because for any reasonable identification scheme, this should in fact be hard, right? And one can show that it lies in between the classical notions of impersonation, but is a bit weaker than the classical man-in-the-middle notion that is often considered in the literature. Okay, So now our main theorem says that if f, this linear hash function, is collision resistant, then the resulting identification scheme, which I showed you a couple of slides ago, has this one more man in the middle security. Okay, so this is what we show in our work. So for this proof, we need some ingredients. Okay, and mostly we follow the proof of Poincheval and Stern, given in their seminal work from Journal of Cryptology 2000. And so notably, this work introduces what is today known as the forking lemma. It's a technique for rewinding an adversary, running it twice, and then getting two answers in order to solve some hard problem. But the original analysis, it used, well, a less refined version of the forking lemma than later given in a generalized version by Bellare and Neven. So it's a very subtle analysis, and it's quite easy to get wrong. And one of our goals was to simplify this complicated analysis and give a more modular proof for it. So the main technical ingredient in doing so is a new forking lemma that we introduce in our work, and we believe it to be of independent interest. So the main thing that we need to do in order to be able to prove this is we need to analyze the distribution of the adversary side output. So what does that mean? Well, consider the very simple example. I run an adversary twice, okay? So it's going to be successful twice, but now I want to know the probability that it outputs the same signature twice, okay? And as it turns out, this is something that we can't infer from the Bellare and Neven generalized forking lemma, because the only thing that the forking lemma by Bellare and Neven would tell us in this context is that the adversary is successful twice, but it can output any two forgeries. And this is why we needed a more general and more refined version of this forking lemma. And this is exactly the type of forking lemma that we introduce here, and we call it the subset forking lemma. And it actually can be shown to imply the forking lemma by Bellare and Neven. And as I said, I think it might also be of independent interest for other works. Okay, so this was the first part of our generic proof framework. Now let's look at how we go from a linear identification scheme to the linear blind signature scheme that we would like to have in the end. Okay, so my starting point will again be this linear identification scheme that I introduced, which follows directly from the linear hash function, right? So now I'm going to convert this into a 3-move blind signature scheme. So the first thing that we do is we replace these two entities here, okay? They were approver and verifier, now they become signer and user. Okay, so now, of course, the signer additionally holds also this message M. But on the side of the prover, nothing changes. So I'm now going to modify the verifier to become the user somehow. So the first additional step that the user is going to do is it's going to sample this alpha and beta, which are blinding parameters. And it's going to use them to blind this commitment that it got from the prover. So now instead of sampling the challenge here at random from the set S, we're going to do something a bit more clever. We're going to evaluate a hash function, which is modeled as a random oracle in our paper. We're going to evaluate this on the blinded commitment, produce this challenge C prime, and then we're going to blind this challenge. And so the blinded challenge is going to be sent over to the signer, and then the signer, as usual, computes the answer S. The check is the same as before. The signature will now become S plus alpha and C prime. And it can be shown, that this is the first theorem, that one more man in the middle security of the identification scheme that I started from is equivalent to one more unforgeability of the blind signature scheme that I have now ended up with here. Okay, this is the main theorem for unforgeability of this blind signature scheme. We also have a second theorem, which is a generalization of works by Schaum and Peterson, which says that this scheme has perfect blindness. So what that means is that the adversary's advantage in linking any of the signatures that result from this protocol to any particular interaction is 0, even if it has infinite computing power. Okay, so here is an example. It's the well-known Okamoto-Schnorr blind signature scheme. So for this purpose, let us consider a cyclic group of prime order P. And we have some public generators, G1 and G2 of this group. And so now we're going to consider the following linear function. So f of R1 and R2, where R1 and R2 are integers in ZP, is going to be G1 raised to the power of R1 times G2 raised to the power of R2. And it's very easy to see, if you're familiar with Peterson commitments, that this has collision resistance if the discrete logarithm problem is hard in the group G. And moreover, of course, it's compressing, because we map from the product of ZP with itself to only this group. So the order of the domain is larger than the order of the range. Okay, so here is the scheme that results from this. Basically, it follows the structure that I showed you. So first you sample these R1, R2, then you compute R by basically raising G1 and G2 to these two exponents here. That's exactly just evaluating F. You send it over, you get back the challenge, and then you compute these two answers here. You send them, and the check is going to be, well, it's going to be multiplying the public key with G1 and G2 raised to these two answers, S1 and S2, right? Okay, and the nice thing is that because our framework is generic, we have not only this instantiation, but we also have an instantiation from RSA and from the factoring assumption. Okay, and of course we hope that we can prove even more instantiations from more assumptions in this framework. So here's a summary of what I talked about. So we gave a generic framework to derive blind signatures from linear hash functions. We capture several important schemes, which include all of the schemes proven by Poincheval and Stern. Our proofs are highly non-tight. They only admit for polylog many signatures, but we show that this is optimal by generalizing an attack due to Schnorr and Wagner. And finally, we introduced this new forking lemma to generalize and simplify a bit the proof by Poincheval and Stern. So here's some open questions. Of course, the main open question is actually the second point, which is to find schemes which admit to sign for polynomially many messages per public key. This has been open for many years, but of course, this is sort of the main goal that we would like to solve. But somehow a bit closer goal is maybe to generalize this framework to also include linear hash functions which have correctness error. So for example, from lattices, okay, or from other post-quantum secure scheme. So this would be another immediate goal for the future. Okay. Thank you.
So there is time for questions. Again, either you need to beat up microphone or we need to repeat the question. So are there any questions? Yes? If you Can you repeat the question?
Okay, so the question was, does this framework work with the Swift hash function? Excuse me. So the answer is it's not clear because the resulting scheme, so why is it not clear? So because it's a lattice-based assumption and we're considering blind signatures here, what we have to do is we have to do this blinding trick, right? We have to add the blinding parameters to the commitment and the challenge. And so when you're considering lattices, usually there is some correctness error involved here. Okay, so maybe you're not in the correct range, and then you have to redo it. And this is something that is not captured in our framework, so it wouldn't immediately follow.
Okay, any other questions? Yeah, Hauck?
What is the limitation to polynomial?
So it's, as I said, oh, sorry, excuse me, yeah. So the question is, where does this limitation come from, which says that we can only sign polylogarithmically many times? So it's not an artifact of the proof, but it's actually something, so there's a concrete attack, and it's based on K-list techniques due to Wagner and Schnorr. So you can really attack the scheme if you do more than logarithmically many signatures per public key. Does that? Okay.
Any other question? Yeah.
Hi, related to that answer, so which part of the proof kind of breaks down? So why isn't the proof that you provided us break down when it's over polylog?
So you're asking about the specific point in the proof, or how the attack
Right,
works?
yeah. So I guess you used at some point that it's polylog, so this proof step works.
Yes.
and-
So the point where it breaks down is so you need to upper bound the size of a certain set. Basically, this is the set. So you have to do this rewinding, right? And so you have to upper bound the probability that you get twice the same output from the forger, because if you get twice the same output, then you cannot solve any problems with this. But because the challenge is maliciously chosen, we can't control this fully. Okay, so now you have to do quite subtle analysis of this, and where it breaks down is where you have to fix all of the challenges that the adversary sends, and there will be L many of them. Okay, and every one of them can be from a very large space, and then we have to fix all of them, and that's where you really need this. So, yeah.
Any final question? If not, let's thank all the speakers of this session again.